Hi class, welcome back. Today we're going to discuss differentials. The objectives for this section is to understand the concept of a tangent line approximation, and you guys will see how fascinating that is. We're going to compare the value of a differential dy, we'll define it as well, with the actual change of y, that means delta y. And then we're going to estimate the propagated error using a differential. And then we're gonna use differential of a function when using differential formulas, and then we're also gonna use this to approximate some values. All right. So what is a tangent line approximation? Well, if you guys notice here, this actually, you guys think about it, is fascinating because back then and sometimes before then we didn't have computers or calculators. So if you needed to estimate such as function like f of x equals 1 plus sine of x for some values, then it required for them to use like heavy formulas to get the exact value instead of just using a calculator, right? But then so what they did is they developed a technique to approximate the actual value by using some differentials. So the idea is that if you're able to know a specific value on the function is the black graph right here, then you can sort of generate this tangent line from there. We can use that tangent line, and we know we can find a tangent line because what are we going to do? They're going to have the same slope, and they're going to have a point in common, and that will be enough for us to actually create this tangent line. And if you guys notice, in this tangent line, you notice like a lot of the points around x equals 0, you're going to be able to be very close to the actual graph, right? The blue line, the tangent line, y values are very close to the y values of the graph, right? They're very close. And so even as you go further, all the way to pi over 4, that's when it starts separating, right? So the approximation starts to, have a bigger error as you go further. But nonetheless, I mean, we did pretty good around here, right? We did pretty good around here. And that's the point, that we're able to approximate the graph values using the tangent line. So let's go back now to the equation. We already talked about tangent line equations so many times in this class, right? And you guys remember how we found it? It was, finding the y equals mx plus b, right? But there was also another equation that we can use, y1 equals x minus x1, right? Like this. And that will give us also the same tangent line. Now, if you notice, this happens to be a point on the graph, this happens to be the slope, and this happens to be the x value. Well, if we know a specific value here, if we know this specific value c right there, then what we're going to do here is we're going to be able to create an equation, right? We're going to be able to create this tangent line, this equation of a tangent line, by using the y value of this point, using the x value of this point right here. So this point right here is let me write it out here. You guys think about it, this is CF of C, right? So we use that point on the graph, and then the derivative of the graph at that x value, and we're going to be able to find the slope of that tangent line, and we're able to find the equation of the tangent line, right? We've done this so many times, right? And so once you find the equation of the tangent line, then you can plug in any number you want, and that will give us the value of the y component of the tangent line. And therefore, you have approximated the original graph. So let's go ahead and try a problem here. So we're going to use the tangent line approximation to find the tangent line approximation of f of x equals 1 plus sine of x at a point 0, 1. So then we're going to use a table to compare the y values to the linear function with those of the original f of x. So what we're going to do is we're going to create this tangent line, and we're going to compare the numbers of the tangent line versus the actual points of the graph and see how close we were. All right, so the point reference that we're going to be using here is at x equals 0. So that's, so let me maybe write it, oops, let me write it like this. That point is x0 and the y value is 1, right? So all right, so here we go. So your c value is 0. Your z value is 0, right? Which is your x value. So here we go. The equation of the tangent line approximation of f at c equals 0 is given up here, right? That equation right there. So f of c plus f prime of c times x minus c. Right. So we shouldn't. It shouldn't be hard for us to memorize it because again, you guys seen this in previous algebra. But anyways, so f of 0. So you replace c with 0. Replace c with 0 and replace c with 0. Easy enough, right? And then you evaluate. What's f of 0? Well, f of 0 is replace 0 for x, and that's right there. So let me put some color here. So this is this right here. And then f prime of 0, the derivative, excuse me, of f of x is cosine. So that's right here. So that's right there. And then x minus 0 is just x, right? So furthermore, we can see here, we can simplify this. 1 plus sine of 0. Sine of 0 is 0. And cosine of 0 is 1. So 1 times x. So you have 1, you have 1 plus 0 plus 1x gives you 1 plus x. And we found the tangent line. So that tangent right there, that tangent line is the equation y equals 1 plus x, right? All right, so let's see how close can we approximate the values of the graph. In this table, you guys will see how we're plugging in numbers that are around this area. So for example, x equals negative 0.5, that will be some number over here. We're going to plug in negative 0.1, that will be a number closer. Negative 0.01, we're getting closer to 0, and then now we're moving to the right side, 0.01, 0.1, 0.5, right? All right. So when you plug in that into the regional function, you get 0.525. For this one, you get 0.9002. For this one, you get 0.990002. This one gives you 1. This gives you 1.0099998. This one gives you 1.09998. And this one gives you 1.4079. But when you do it for the approximation, right, for this tangent line, which is trying to approximate these values, we see that we get 0.5, right, which is kind of off, right? But then we get pretty close over here, right, 0.9, and we get even closer right here, and then we get closer here. We're pretty close here, we're getting further apart. So what we're saying here is the closer you are to the point of reference, which is in this case x equals c, the approximation, the error will be smaller, right? Let me say that again. The closer you plug in numbers of x into the tangent line, they're closer to this point of reference, which is x equals 0, the error of y will be smaller, right? And it kind of makes sense because you're closer to this point of reference. Anyway, so that's the concept that we're trying to do here with this approximation. We're gonna come back to this idea in the last problem, so hold on to that. We're gonna move on to differentials. So we kind of discussed a few items or topic or items, yeah, from the last problem that are sort of now we're gonna be able to define them. So we have this special graph, where we have this graph f, and we said that we are able to approximate this graph f with a specific tangent line, right there, this blue line. And what we're saying is that that we're able to compare, right, that these values are very close to each other, right, very close to each other. But we said that as further you go from the point of reference, which is c, the further you get, the error becomes bigger, right? So what we're trying to say here is that we can kind of label some of these items. And so what we're going to say here is that the difference between this point in the y component, right, if you have f of c here, this is f of c, and up here you have f of c plus delta x, the difference between those two, we're going to call that the difference of y. The difference of y, we're going to call that delta y. If you notice here, that this difference is a little bit bigger than this difference right here. But what is this right here? Well, can we compute this? Yes, it actually depends on your tangent line. In fact, this right here happens to be f prime of c times delta x. The derivative of f at c times delta x times the difference of that. So if you notice here, if we know c and we know the function, we don't actually have to know, we don't have to calculate f of c f of c plus delta x. We can approximate it by just taking the derivative of the function here, plug in c, and then multiply by this difference, right? By this difference, which is delta x. All right, so that's what we're trying to say here. So this let's formalize this here. So when we have a tangent line to the graph of f at the specific point of reference c and f of c, we can create this tangent line for the equation, for the tangent line. So here I want to make sure that this is clear. There is a prime in here, right? There's a prime. And we use this as an approximation of the graph of f, right? We use this tangent line as an approximation of f. And the quantity x minus c, right? The quantity x minus c will be called the change in x, which is denoted as delta x here. So this letter right here, this is a triangle, but it's a Greek letter d for difference, and it's pronounced delta, or it is named delta x. So delta for d and also d for difference, right? Delta x. So that's the difference between x and c, as shown in the figure. But when delta x is very, very small, right? If this number is very, very small, right? That means that these points are closer and closer to their point of reference. Then we can say, hey, the change in y, right? The change of y can be denoted to be it's going to be denoted to be delta y, but it can be approximated. The difference of those two can be approximated by multiplying the derivative of f at c times delta x. So as long as delta x is close enough, this number, let me put this into two different colors. This value right here versus this value right there can be approximated. We can approximate it, right? If delta x is close enough. We're not saying that they're the same. We're just saying that we are going to be able to approximate it, right? And that's a big deal. I mean, maybe we're not seeing it right now, right? But we're going to see that's a big deal. So for such approximation, we often call this delta x. Delta x is denoted traditionally to be denoted as dx. And this is a differential of x. So the difference of x and c, is delta x, right? But we also refer that in this case, because it's very small, that delta x is also going to be referred to differential of x. Now we can say the same for the y's. So for the y, the expression f prime of x times differential of x is denoted to be dy. So this is denoted to be the differential of y, which is differential y. Now if you notice, what we're saying here, pretty much what we're saying is that this is known as the differential of y. So therefore, the differential of y, by associative argument, is approximating the delta y. So pretty much this is what we're saying. We can see over here, we're saying that delta x is very small, so that's going to be the same as the differential of x, right? Those two will be the same. But for the in terms of y, it's not going to be the same. The delta y will be approximated by the differential of y. So these are the same because they tend to be small, but these are approximated, right? And so therefore we can say in general that delta y will be approximated by f prime of x, differential of x. So the definition of differentials, let's look over here. Let y equal f of x represents a function that is differentiable on an open interval containing x. The differential of x, denoted by dx, is any non-zero real number, and the differential of y, denoted dy, is equivalent to this. So by definition, this is our differential of y. Now, if you guys notice here, this is silly, but if you guys notice, think about this. Let me write this. Differential of y is f prime of x times delta x, right? That's what we're claiming. So look at this. Look at this. So if you decide to divide both sides by dx, what do we get? Do you see? Do you see where that came from? So differential of y is by definition f prime of x dx, because we know that derivative of f in respect to x is dy dx. So I hope that you guys can find that so a good way for us to remember the relationship between the differential and f prime of x dx. All right, so we're gonna use the next example to compare both delta y and differential of y. So here we go. All right, so compare delta y and differential of y. Let y equal x squared. Find dy when x equals 1, and find dx when x equals 1 and when dx is 0.01. And then compare this value to the actual delta y for when x equals 1, where delta x is 0.01. All right, so here we go. We'll start with the differential y. So for differential y, we know that by definition is equal to this. So we have f prime of x dx. So we need the derivative. So let me make it more obvious there. All right, the derivative of f at x equals 1, and then multiply by delta x. Right, and all right. So what do we have? Well, the derivative of f is 2x. So this part right here, the derivative of f is 2x. So it's 2 times x, which in this case is it's just 1, right? So this will be plug in 1 here, plug in 1 there, and that gives us 2 times 1, and that's how we got the 2, followed by the 0.01, and that gives us 0.02. All right, so pretty much all you have to do is compute this. For delta y, the definition of delta y, which we have to be clear, right? It is the difference between your f's, right? Your y's. So the way we're gonna do it is we're gonna say the difference between y's is f of x plus delta x minus f of x, and we're gonna say, okay, well, what is x plus delta x? Well, all you have to do is add x to delta x, right? Add x to delta x. So 1 plus 0.01 will be 1.01, and then you're gonna plug it into the function, which is a square function, followed by the minus, followed by f of x by plugging in x is 1, so plugging 1 into f, and then f of 1, well, f is the square function, so we're going to square that 1. Simplify that, and that gives us 0.0201. And so the difference between those two is minimal, right? And we can see that in the picture. Here's the original function, x squared, but here is the linear approximation of a tangent line, right? And we see that difference between those two is minimal, but because we're zooming in. But anyways, that's sort of the idea. All right, so let's use this in an application problem. So the way we use this in this problem is by using and defining what's known as a error propagation. All right, so the way I understand propagated error is the accumulation of error from a measurement, right? So if you ever try to compute something or create something, well, everything is going to depend on your measurements. Now, obviously, we're not perfect, so when you are going to measure something, you're going to measure you're not going to measure accurately. So there's going to be some error that you're going to bring to your formula because of your faulty of measuring correctly, precisely. So that error that you are bringing back from the measurement, when you put it into the formula, it's gonna propagate into the formula. So there is gonna be some error. Anyway, so that's how I understand it. So if you let x represent the measured value of a variable, and let x plus delta x represent the exact value, so the measured versus the exact value, then delta x happens to be the error in measurement. All right, so if you measure x but the actual number is this, well, you are far away from this, right? You're this much of an error. And so finally, if the measure value of x is used to compute another value in the formula of f of x, then the difference between f of x plus delta x and f of x is called the propagated error. So in other words, we say that the error between the exact measurement, right? This was the exact measurement when you put in the formula. This will give you an exact value versus what the measurement they use, the one you measure, right? You measure this, but this had some error. Anyway, so when you put it into the formula, you're gonna create an error overall, but the difference between those two is gonna be defined to be the propagated error. So think about it as the propagated error is the error at the end of the problem, right? Okay, so estimation of error. The measure radius of a ball bearing is 0.7 inches, as shown in the figure 3.68 right here. If the measurement is correct to within 0.01 inch, estimate the propagated error in the volume V of the ball bearing. So we already know that this is the propagated error. Now, we don't have the function here. So, I mean, we only have the volume, right? But they're only asking us to estimate it, right? To estimate the propagated error. So we can estimate the propagated error of the volume by looking at the volume here, right? We know that this is going to be the volume of the sphere, where r is the radius and r is 0.7, and the margin of, or the error of measurement, is within 0.01. And that is because of this, right? It was within, your error is within like this, right? Your error is within that, and so we can think about it as a number that at most is going to be 0.01, and at least it's going to be negative 0.01. So that's why we're only going to use this right here. So we're going to use the dramatic difference, right? All right, so we often just use this, right? So this is what we're going to use. So the propagated error is defined to be delta V, but we're looking for the estimation. So we're okay with just having the estimation of delta V, which is going to be the differential of V. So let's compute the differential of V. The differential of V can be found by taking the derivative of V in respect to R. So we're going to have to use the chain rule, right? So it will be 4 over 3 times pi, and then r 3r squared times dr. And so if you notice, it's important for us to keep the dr here, because that's going to be the error. And then so we have 4, so we simplify those by canceling the 3's, and so we're left with 4 pi times 0.7 squared times plus or minus 0.01. And then by computing this, we get plus or minus an approximation of plus or minus 0.061 plus or minus 0.06158 cubic inches. And so that's the propagated error, an approximation, right? Now, if we think about this, right, so this is the answer. That's what they were asking us to find. But let's go further, because let's think about this. This number, what does it mean, right? What does it mean? I mean, it's an error, but it's very hard for us to put to make a conclusion about this error, because we don't know how big the volume is, right? We don't know how much is this compared to the actual volume. So this actually brings a different type of writing this error. This is known as the relative error. So the relative error says that we are gonna describe the error relative to the actual volume. So a lot of times we say, well, this does not provide a good context of the error. That is this a small or a big error? Thus, it is better to make this error relative to the actual volume. So what we're going to do is we're going to take the propagated error and divide it by the actual volume. So we have the propagated error, 4 pi r squared dr over 4 over 3 pi r cubed, simplified by canceling the pi's, canceling the 4's, canceling r squared with the two of the r cubes. So we're left with the dr, we're left with 1r, one of the r's, and 1 over 3. Well, if this is a fraction over a fraction, then we can multiply this by the reciprocal, and that's how we get the 3 on top on the numerator. So 3 times dr over r is the in this example the relative error. So now all we have to do is plug in our error of measurement, which was plus or minus 0.01, and plug in our radius, which is 0.7, and so this will give us a relative error of 0.0429, which means is actually we can write this in percentage as 4.29%. So you guys see here, this gives us a better context of what the error is. So the volume has a propagated error of about 0.06 cubic inches, but it has a relative error approximately to be plus or minus 0.0429, which is called the relative error. Or we can call this percentage error by writing it as a percentage form, by moving the decimal. All right, so that's one way we can apply this. Now, in the next example, in the next topic, we're going to talk about calculating differentials. Now, this becomes a very important part, especially when we move on to integrals later on. So it's important for us to practice this. So differentials, right? We're going to be able to find the differentials. We already know what the differential is, right? Differential is this dy times the derivative of the function times dx, right? So the way we're going to do this is by using something that we already knew. So what we're going to do here is, this is very familiar, right? We're just going to take the derivative, right? But we're going to write this as dy dx, and the derivative of this will be 2x. The derivative of this, right, will be dy over dx equals to negative 1 over 2x to the 1/2, right? We can see that. This will be dy dx equals to 2 cosine of x. And this one we have to use product rule, which will be negative x sine of x plus cosine of x. And this one will be dy dx equals to negative 1 over x squared. So this is the derivative, but the differential needs to be in this form. So what we're going to do is multiply both sides by dx. There you go. Multiply both sides by dx. There you go. Multiply both sides by dx. There you go. Multiply both sides by dx. Well, we're going to multiply the entire right side by dx. So put parentheses, multiply by dx. And then lastly, multiply both sides by dx. And there you go. So that's it. You found the differentials. Right? So let's not overthink this problem, right? We're just finding the differentials, and the differential by definition of y is f prime of x dx. Now this notation is thanks to one of the founders of calculus, Leibniz, which he was a German mathematician, and he was said to invent calculus in the same time as Isaac Newton. So a lot of times when we think about differentials, we can think about it actually as being a chain rule process. And so when as you guys will see here, I'm going to approach differentials in a different way. So I'll take the derivative, right, f prime of x, the derivative, find the differentials of a composite function. So what we're going to do is we're gonna treat this as a as pretend that we're doing chain rule. So it's going to be like the way we did in the table. So we have f prime of x equals the derivative of the outside, which is cosine, leave the inside as it is, and then multiply by 3. The differentials of this is just differential of y and then multiply by dx. So it will be dy equals f prime of x dx. So multiply your f prime by dx, and that's it. Take the derivative of this, right, by using chain rule, bring down the 1/2, multiply by x squared plus 1, take away 1, multiply by the inside of 2x, simplify, which gives you x all over x squared plus 1 to the 1/2, and then the differential of this will be dy equals f prime of x dx. So just take f prime and multiply by dx, and there you go. And so that's how we take the differentials, right? So I really want you guys to think about the difference between delta y and differential of y, right? That's the difference that we have. That's what we're trying to use here. The difference between those two, right? The difference between those two. So remember that one of them. So the difference between both of them is that delta y is f of c plus delta x minus c. So is the actual difference of the y's, versus dy is just an approximation. And then we rewrite it like this, right? Or we can write it also with the delta x, right? All right, so that's the only difference, right? We like I said before, delta x and dx tend to be always the same. And so that's the difference between them, and what we're saying here is that those two can be calculated. All right, so we're going to go ahead and use again this equation. So we're going to go down to the last problem and use this tangent line, which is f of c plus f prime of c times x minus c. All right, so in this problem, we're going to use differentials to approximate a function value. To do this, we're going to recall back to y equals f of x using the formula which is derived for the approximation. What we're saying here, as we said before, we can approximate delta y with dy. And we're going to use this formula to choose the values of x that makes the calculation easier. So for example, if they ask me to approximate the value of the square root of 16.5, well, I can guess that the number is going to be around 4, right? But how accurate can I be, right? So what we're going to do here is, it's fascinating. We're going to actually be able to get pretty close to the actual number, right? So what we're going to do here is we're going to use this equation right here. We're going to use this equation to approximate our value, right? So here's our f, our function, and then if you guys remember from the tangent line, this is the approximation of this was f of x plus f prime of x dx, right? So or you can just see it from here, right? If you think about it, if you add this on both sides of the equation, then what you have here like this, right? That's sort of what we have, right? But remember that this is f prime of x dx, right? So that's how we can come up with this equation. I don't memorize it. I think about the linear, the tangent line, right, all the time. So All right, so we're gonna write this f of x is f of x. F prime of x is just a derivative of this, which is right here. And I believe this needs to be, this is going to be, yeah, good. And then multiply by dx. All right, so we have everything. So now what we need to do is we need to choose our x value and our delta x appropriately. Well, if you notice here, what we're going to be end up doing is we're going to take the square root of a number here and there. So looking at this, 16.5, right? Think about 16.5. Can you think about what will make this number like a nice perfect square, right? Well, 16, right? Do you guys agree with that? Well, it would be nice if this is 16, right? If that's a 16, so that means that this needs to be a 16. So your x needs to be a 16, and that means that the delta x will be 0.5. So x is going to be 16, delta x is going to be 0.5. So now we can go back and say, okay, f of 16.5 is equivalent to f of 16 plus 0.5, which is approximately the square root of 16 plus 1 over 2 times the square root of 16 times 0.5. If we compute this, the square root of 16 is 4 plus 1 over 2 times 4, which is 1/8, times 1/2. So this is 4, and this is 1/16. Combine this in your calculator, and that gives you 4.0625. And there you go. Do you guys see how that was kind of nice? It was kind of neat, right? To be able to do this approximation. In fact, if you guys try this in your calculator and try this actual square root of 16.5, the number is the actual number is approximately, right? I'll use the same number of digits, so 0.621, right? So we're pretty close though, right? It's pretty nice. All right, so in the same argument, we can say, well, what about, so we're done, right? That's the actual problem. But we can actually further just extend this analysis of this problem and say, well, what about if we ask to find a tangent line? A tangent line, yes, a tangent line, that a line that will help us approximate for more numbers, more numbers, right? Well, all we have to do is use the same equation, but just leave it in terms of x. So here we go, right? So I'm using the same tangent line, y equals f of c plus f prime of c, x minus c. Well, here's my point of reference, which is 16, 16, x minus 16, and then which is the first equation that we use. And then if we simplify this gives me 1/8 x plus 2. So that's how we got this equation. And then you can try numbers, right? Now you can just plug in 16.5 into this equation, and we end up getting this, right? So we're able to approximate this further. Awesome, right? So I think this is a nice, great topic for us to conclude the chapter. It's we explore many applications of the derivative. This was just a cherry on top of the pie, right? The cake. All right, I hope you guys enjoyed this lesson. Please let me know if you have any questions, and I'll see you guys next time.